All right, hello everyone. This is the Level 2 Electricity and Magnetism paper from 2024. If you're following along, make sure you've obviously got your resource sheet, calculator, and a pencil with you. And we'll jump straight in. So, question one is about parallel plates. We're told there is an electric field between two parallel plates 0.06 meters apart. On the diagram below, we are told to select one of the 12-volt cells labelled A and B and correctly connect the cell to the plates so that it produces the field shown. Now, in this diagram, we've got these two plates with lots of field lines. The field lines are going from the top plate to the bottom plate. With electric field lines, they show the movement of a positive charge in that electric field. And so this field diagram is telling us that a positive charge would move from this side to this side. Therefore, this must be a positive plate and this must be the negative plate. In order for this to be the positive plate, it must be connected to the positive terminal of the cell. Now, cell A has the positive terminal at the top and the negative terminal at the bottom. Sorry, it's a bad plus. And then here it's inverted upside down. Okay, we want this side to be positive, and so we're going to use cell A. And you quite simply draw a line. It doesn't have to be particularly neat. I'm going to use a ruler just because, and make sure you connect it up to both sides. And just make double sure that you have got one continuous line, there are no gaps. Okay, that's easy as that. For part B, we are told that an electron is released from the negative plate. Ignoring the effect of gravity, calculate the speed of the electron when it reaches the positive plate. Now we're told that we're releasing an electron from the negative side. Electrons are repelled by this side and attracted here, so it's going to move across the field towards the positive plate. We are told, that the two plates are 0.06 meters apart and we have a voltage of 12 across our two plates. To work out the speed of the electron, there's going to be three steps here. We want to end up calculating V. Now, in order to do that, we need the only way we can link the two aspects of mechanics and electricity together here is to consider the energies. And so we're going to use kinetic energy, and we're going to say that that kinetic energy arrives from the electric potential energy, which in turn needs us to work out the electric field strength. Okay, so it's a bit of a process, but it's just using one equation after the other. Now, from our resource sheet, the equation for field strength of an electric field is equal to voltage over distance. I don't know why I'm still using pencil, I'm going to use pen. Is voltage divided by distance. We're told, as before, the voltage was 12, the distance was 0.06. Working that out with a calculator should give you 200 volts per meter. Now, because we're going to be using each of these answers again and again, it's important not to round whatever answer you get. If you get a completely rounded number in your calculator, then that's fine. Once we've done that, we are going to work out the electric potential energy. The equation for that from our resource sheet is delta EQ. I forgot to open mine, so I'm going to do that now. Is EQD, sorry. Or the equation is delta EP, my mistake. Is equal to EQD. We've just worked out E. We're talking about an electron, so we're going to use the resource sheet's value for the charge of the electron, and the distance covered is again the distance between the two plates, 0.06 meters. So we're going to put all those numbers in together and we'll work out our answer. Times 1.6 times 10 to the minus 19 times 0.06. And that gives us 1.92 joules times 10 to the minus 18. Now, to work out our kinetic energy, we just have to use the fact that energy is conserved. In the question, we are told to ignore the effect of gravity. So we haven't got to worry about the change in gravitational potential energy. We can just say the kinetic energy must be the same as our delta EP as energy is conserved when there are no external forces. And I'm going to run out of space, so I'm going to start using half lines. If we know that our two energies are equivalent, then we can write that our kinetic energy, the kinetic energy equation, is half mv squared must be equal to the value we've just worked out, 1.92 times 10 to the minus 18. And then we're going to rearrange this in order to get an equation for velocity, where v is going to be equal to the square root of 2 times 1.92 times 10 to the minus 18, divided by the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms, again from the resource sheet. If you're unfamiliar with the rearrangement, I'll just quickly do it with the EP symbol rather than the standard form answer on this left-hand side, just because it will save time. So half mv squared is equal to EP. Then we have to times both sides by 2. So mv squared equals 2EP. Then we have to divide by m to get it on its own. So we get v squared is equal to 2EP over m. And then you can square root everything like that. And that is not very easy to read, but hopefully you can freeze it and pause it and follow along in your own time. Once we've got this, you're going to type this all into a calculator and get your answer, and you should get 2.1 times 10 to the 6 meters per second. Now I should have said before, connecting these two terminals up was an achieved question. Part B, this had excellence. Excellence was available, if you got the full correct answer. If you found a value of V following this method, but you got a different answer because there was a mistake earlier on, you can still get merit. If you get to this working out the potential energy and then you can't go any further to the kinetic and then velocity, this is again just equivalent to merit. So just doing these first two steps, if you work out the electric field strength, that in itself is an achieved mark. We've only got two values in this paper so far, so hopefully you're able to use them and spot the equation that you should have used for them. Okay. Now for part C, we are told that an electron moves into this field from left to right. On the diagram below, again ignoring the effects of gravity, draw the path of the electron inside the field. Now again, the field lines are following the same direction as before, so I'm just going to add a quick label just to make it super clear to myself which one's the positive, which one's the negative terminal. Now we know that the electron will be attracted to this top plate and repelled by the bottom plate. However, it's not just going to immediately go in and move upwards, it's going to have this nice parabolic curve. And so we'll come in initially horizontal, slowly turning upwards until it collides with the positive terminal. Now this is a merit question as long as you have this is a merit question with the description on the next page. For this diagram, you just have to have this parabolic curve going upwards and hitting the positive plate at some point along there. It doesn't actually specify in the mark scheme whether it needs to hit the plate. If you drew it so that it was maybe coming out the other end with a slightly curved trajectory, I imagine that would be correct, but yeah, good idea. Unless it specifies anything else, just make it hit the positive plate. Now, the second part of this question, where you can get the merit points for, you are told to use physics principles to explain the path that you have drawn. Your answer should refer to any relevant forces acting on the electron, including giving their directions. Okay, I'm going to do this as bullet points because you're allowed to do that in these exams, and it makes it a bit easier to follow as well. So like I said before, we have electron is repelled by the negative plate due to, and then we're going to name the force here. There's a few different ways you could describe it. I'm going to describe it as the electrostatic force due to the electrostatic force. In the mark scheme, they use the term electric force, which would be fine as well. Now, we've said that it's been repelled by the negative plate. It's also is attracted by the positive plate. Due to the electric force again, because it's asking us to refer to, when it's saying to refer to any relevant forces, it means naming them, and we have to remember to give the directions as well. I know we're saying repelled and attracted. I'm going to say, so the electron will move upwards in a sec. Electron is attracted by the positive plate due to electric force, bad English, due to the electric force. So the electron experiences a force upwards. And we're going to say that the size of the force of the net force is constant. Because we're talking about a uniform electric field, we can use the equation F equals EQ if Q is unchanged because it's an electron, and if it's a uniform electric field, both of these sides are staying the same, so the force will also stay the same. Now, if you give all of that, that is a merit answer with the drawing on the previous page as well. If you just had any one of these points or the diagram on the previous page, that would be achieved in itself. Okay. Now for part D, we're talking about Millikan's oil drop apparatus, which is just a specific example of an electric field, a uniform electric field. We've got a little diagram to show us, and I believe these little grey patchy bits are meant to be the oil drops. We are told that a simplified version of Millikan's oil drop apparatus shown below. In his experiment, Millikan placed negatively charged oil drops inside an electric field and adjusted the voltage across the plates until they were held stationary. On the enlarged diagram below, add labelled arrows to show the two forces acting on the negatively charged oil drop to keep it stationary. Now, an electron, these oil drops have mass, therefore they experience the force due to gravity. The actual length of your drawing doesn't matter here. So I'm going to draw it as a downwards arrow, and I'm going to label it force with gravity in subscript, just to make it super clear. Weight, G, W will probably be fine as well. We are told that the oil drops are held stationary, so there must be some force balancing it, and it's the electric force, the electrostatic force. The only stipulation with the size of the arrows here is they have to be the same as each other, equal but opposite, because it's being held stationary. So as best you can, you could have used a ruler for this if you were keen, but just eyeball it best you can. Arrow the same length going upwards, labelled F, electrostatic. Again, electric or just E would probably be fine as well. That in itself is enough for achieve, because this is another part I and part I. Oh, sorry, wasn't on the page this whole time. My mistake. The diagram should look like this, with the two arrows the same length. My mistake. Doing this would be enough for achieved in this question D. Part 2 on the next page is where we can earn some more excellence credit, I guess. So yeah. Part 2. In one experiment, an oil drop of mass 1.95 times 10 to the minus 15 kilograms with charge Q was held stationary between the plates as below. This is our drop here. We are told to calculate the number of excess electrons on the oil droplet, giving your answer to the nearest whole number. So with these oil drops, just in case we have forgotten, I'm going to try and draw this zoomed in on, sorry. This is our oil drop. The oil is given extra electrons, which gives it an overall charge. And so we can sort of think of it looking a bit like this. The number of extra electrons it has determines the size of its overall charge, which is why this is an unknown here, and determines how much it interacts with the electric field. Now, to work out the number of excess electrons, we need to work out the total charge. You can't see that. The total charge, and then we'll work out the number of electrons. I'm going to call that N. Based on our previous drawing on the previous page, we know that the two forces acting on this oil drop are Fe and Fw. Now, these two, badly drawn, should be the same length, so they should be equal to each other. And so I'm going to start my working with a pen of force of W must be equal, with an exclamation mark, to the force of the electric field. Okay. Now, to work out the strength of our electric field, we're given the voltage and the distance between the two plates again, and so we can use the formula mg is equal to the force of the electric field, which is equal to EQ, E being equal to V over D. Now, you can just do this in separate stages. I'm going to do it all together because it's a bit cleaner, I think. But yeah, you can just work out the electric field strength, then put it into the equation for force, and then equate it to weight. Completely up to you. In this diagram, we're told that the distance is 2.19 centimeters. I probably should have gone and immediately converted it. I'm going to do that now by dividing it by 100, because there's 100 centimeters in a meter. Now, we get to put all these numbers in, and it'll allow us to work out our charge Q. With our equation, mg is equal to V over D times Q. I'm going to rearrange it to get Q on its own. Q is equal to mgd all over V, just by timesing both sides by D, and dividing both sides by the voltage. And we get this equation. Now, we are told that the mass of the oil drop was 1.95 times 10 to the minus 15 kilograms. I'm going to put that number in straight away. We are multiplying it by the strength of gravity, which we are told to use 9.8 for. And we've just worked out what our distance is in meters to be 0.219, and then we put that all over the voltage, which we are given to be 6.54 times 10 to the 2, or just 654. But you don't need to worry about converting it, just put it in and the calculator will figure it out for you. Once you've done all that, you should get yourself a charge. Actually, I have no idea. 1.95, that's a 695 times 10 to the minus 15 times 9.8 times 0.0219, all divided by 654. And it should give you 6.4 times, 6.399 times 10 to the minus 19. And because this is our charge, our overall charge Q, we're measuring that in coulombs. So now we have our charge total as, I'm going to round it to 6.4 times 10 to the minus 19. Hopefully you can see that 6.4 is about 4 times bigger, or 6.399 is about 4 times bigger than the charge of the electron. To work out the number of electrons, we're just going to do 6.4 times 10 to the minus 19 all over 1.6 times 10 to the minus 19 equals 4 electrons. Okay. Now that is our final answer. If you do all that correctly and get 4, that is excellent. If you find the charge, the total charge, or you have the correct arrows on the previous page and have worked out the electric field strength just by doing E equals V over D, so not getting stuck into all this force stuff, just by working out the electric field strength, that will give you your merit. Or if you work out any charge and try to divide it by the charge of the electron and get a whole number, and coupled with the drawing on the previous page, that is also merit. Or if you basically do any one step in this correctly, sort of up to here, if you worked out the weight of the electron instead, that would be achieved. Or if you just did the arrows, that would be achieved. Or if you just worked out the electric field strength, that would just be achieved. And that's question 1. I'm sorry about that. My laptop demanded an update, but we'll go back over it again. Question 2, circuits. This is going to be about a combine harvester. Obviously, there's no photo of one, there's meant to be one there, which is why it's talking about harvesters here. Modern harvesters contain many warning lamps. A simplified version of a circuit connecting some of those lamps is shown below. We've got a circuit here with a cell running 12 volts. We've got a little variable resistor, and then we've got these 3 light bulbs arranged in a parallel couple of loops down at the bottom here. We are then told the circuit has 3 identical lamps labeled B, C, and D. What that means is that the resistance of B will be the same as C and the same as D. You don't need to draw that out necessarily, but just to remind yourself in case you forget. A dimmer switch represented by the variable resistor is initially set to 3.5 ohms. When all the lamps are operating, the current in lamp D is 1.4 amperes. Part A asks us to explain why the current in lamp B is 0.7 amps. As I said before, this little parallel section is significant. If you remember your rules for the 2 different types of circuit, in a series circuit, the voltage is shared and the current is the same everywhere. In parallel sections, however, it is the voltage that's the same across each parallel loop. So the voltage for B and C, for both of them, will be the same as the voltage received by bulb D. What is shared in parallel is the current. And so when the current comes along through our circuit, it gets to this point here, some of it goes left, some of it goes right. The amount which goes in each direction is dependent on the resistance in that section. Because B and C have twice as many light bulbs in that section, there's twice as much resistance from V equals IR. If there's twice as much resistance, it means we're going to have the smaller current, about half as much current, if our voltage stays the same. So if that times is by 2, this times is by half. That wasn't as easy as I thought it was going to be. Okay, so we can start explaining it. The fact is, across both parallel loops, the voltage will be the same. The loop containing B and C has twice the resistance than the loop containing A Therefore, if lamp B has got 0.7 amps of current, if lamp D has got 1.4 amps of current in it, lamp B will have half the amount because that branch has twice the resistance. Therefore, B will have half the current of D. Therefore, current in B equals 0.7 amps. Okay. Now, if you did write all of that, that is a merit answer. If you just said that either the voltage is the same on both branches or that the resistance is twice as big in one branch, then that would be achieved. Doing both and explaining your answer fully gives you merit. Now for part B, we are told to show that the resistance of a single lamp is 3.3 ohms. Now, this is going to be quite a lot of calculation. They don't seem to have given us much space. This will be an excellent answer. So I'm going to try and keep it as compact as possible. But the part A has given us a bit of a helping hand. The reason it was to show that or explain that is because you need this 0.7 for part B. Now, if we're interested in working out the resistance in one of these light bulbs, we also need to work out how much voltage is going through each loop. Because each loop will have the same voltage, we still need to work out how much of the 12 volts is being received here. Because some energy is being used to go through the variable resistor, we'll have to work out how much voltage is dropped over this resistor to work out the amount of voltage left for this entire section. Then we can use Ohm's law and the various resistance equations to work out our resistance. Bit of a job, it's not so bad. Here we've said the current in lamp B in this section is 0.7 amps. Oh, please don't unfocus. And we were told that the current in lamp D was 1.4. That means once the two loops have recombined here and before they split, there will be a current of 0.7 plus 1.4, 2.1 amps. Okay, that's our first step. I circuit, the current in the circuit is equal to 0.7 plus 1.4, equals 2.1 amps. Once we've worked out the current in the circuit, we know what the resistance of the variable resistor is, and so we can use Ohm's law. So V of the, I do apologize, V of the, what do they call it? A dimmer switch. So V of the, I'm going to call it variable resistor. I'm going to call it dimmer. Have less V's and R's. V of the dimmer is equal to IR equals 2.1 times 3.5 ohms, because that's how much the resistance is of that variable resistor at that time. You're going to work out the answer to that. 2.1 times 3.5 gives us 7.35 volts. To work out the voltage through the parallel section, I think I was pointing up here before, the 12 volts has been split between these two sections, the variable resistor and the parallel section. So the voltage here is 12 minus 7.35, giving you 4.65. Apologies for that. Once we know the voltage through this parallel section, each loop, this upper one and this bottom one, will both have a voltage of 4.65. We know the resistance of D here is the current through bulb D is 1.4 amps. So we can use Ohm's law. VD equals ID RD, just to make it clear that I'm talking about those values. Rearranged gives us RD is V over I. Oops. The voltage is 4.65. and our current was 1.4. Doing that calculation gives you 4.65 divided by 1.4, 3.32, 14 ohms, and then we're going to round it to 3.3. Because this is a show that question, you must give your unrounded answer and then the rounded answer. If you just write 3.3, even though it's the right calculation, they will normally demand the unrounded answer as well. Sorry. Now, alternatively, once you've worked out you can, instead of working out the voltage and then the current through D, sorry, I can't get ahead of myself. We said before that all three resistances of the light bulbs are the same, and so if you've worked out the resistance of D, you've also worked out the resistance of B and C as well. If you want to do this a different way, you can work out the total resistance of the circuit by using the fact that your total current is 2.1 and your total voltage is 12. You know that 3.5 ohms is in series with this combined section's resistance, and once you've got that, you can use the parallel resistance equation to work out the individual contributions from a light bulb in there. It's a bit more difficult with the algebra, but I mean, similar sort of question. This is the easier way, and you get 3.3. If you did all of that correctly, that is an excellent question. If you got to the point of 4.65 volts here, or in the alternative method, if you worked out the overall circuit resistance, which would be 2.21 ohms, that would be merit. If you just got to this circuit current stage, 2.1 amps is achieved. That was the first step for both of them. 3.3 for your. Now part C, the camera won't focus on it, but hopefully you can see your own one. Explain what would happen to the brightness of lamp D if lamp B were to stop working. Now, in order for us to explain this, I'm going to go back to the previous page. Annoyingly, I can't fit both on the same page. Which way around is it? Sorry. Lamp D, if lamp B were to stop working. So I'm going to start annotating. If lamp B were to stop working, I'm going to scribble it out in a different color. Lamp B were to stop working, electrons will be unable to flow through this upper loop. All the electrons will have to go through bulb D. Therefore, the resistance of the circuit is going to increase. As the resistance increases, it gets harder for the electrons to flow around the circuit. It becomes a series circuit now, which means that the resistance has gone up, the current will decrease. Because we haven't changed the voltage that's being supplied, if it's harder to get around the circuit, the electrons will just go around at a lower rate and a lower current. Now, with a light bulb, its brightness depends on its power, and power is a combination of voltage and current. If we're saying that the current has gone down, but the voltage has gone up over light bulb D, what actually happens is they don't cancel out. The way that the current decreases, it decreases less than the voltage increases. It's an important thing to remember, which means that the power will actually increase. It doesn't stay the same. The two changes don't counteract. The voltage going up has a bigger influence than the current going down. And so the power through bulb D will increase. And it's because the circuit goes from containing a parallel element to just having a series section there. Okay, I don't know if that's easy to see or not. On the other side, we do our best to remember all that, and then we go answering. And it will focus once I start writing, I think. If B stops working, current can no longer flow through that loop. The circuit goes from parallel to just series. Before it was a complex circuit, it was a combination of both. Now it's just things in series. So the circuit resistance increases. Okay. And because the circuit resistance has increased, the circuit current and the circuit current decreases. I'm going to start a new paragraph here. Total input voltage is the same but the bulb D receives a greater share of the voltage. And so now we're going to say power determines bulb brightness. We're making lots of points. We're going to tie them all together in the last sentence. Power determines brightness of bulbs. And I'm going to put in here that power is equal to P equals IV. And then you're going to say increase in V is more significant than decrease in I. So power increases and brightness does too. Whoops. Now you can actually calculate this instead. The mark scheme accepts full credit if you work out the precise answers. To do that, just quickly, you have to work out the initial power through bulb D as it currently stands. You've just worked out the voltage through it, and we worked out the voltage through it. We've got the current through it, so we can work out the starting power, and you can then work out the power after this has become a circuit, and just a plain series circuit with these two components in alone. Doing that, you'd get that the power before the change was, or before the break, was 6.4 watts. Afterwards, it was 11 watts. So the maths would actually prove our sort of nebulous statement that the increase in voltage is more important than the decrease in current. So that's an absolutely fine one. If you have this full description or the full calculation demonstrating that the 11 is bigger than 6.4, that is excellent. If there's a series of statements you can make, which are the fact that the current increases, or less current, or the total voltage stays the same, or the voltage across the light bulb gets bigger, or power determines brightness, or lamp D has more voltage, therefore gets brighter. If you had any two of those points, that would be merit. If you just had one of them, sorry, that's not true. Or if you made a mistake in your calculations, one single mistake, that would be merit. If you made any statement saying that the total resistance goes up, or that it's in series, that would be achieved. Doing both of them together would be merit, as before. So a bit of a job, a bit of a weird explanation. The maths does prove it, but yeah, this is the written explanation. If you want to have a look at the calculation, it is on the mark scheme. Then part D, we are told that miraculously bulb B has come back to life with all 3 lamps working again. The variable resistor is adjusted so that lamp D converts 530 joules of energy into light every minute. Calculate the total current in the circuit. Start by working out the power of lamp D. So we've now got a system where suddenly all the values from before have changed. Now we're given a bit of a hint that we should start by working out the power of lamp D. We know that there's 530 joules converted into light every minute. Now 1 minute is equal to 60 seconds. If we don't use minutes in our calculations, we are going to use seconds. To work out the power of D, PD, is equal to energy over time, which comes from the equation on your formula sheet. E equals PT. Probably should have written that first, didn't. My mistake. Power is energy divided by time, which is 530 divided by 60. Pop that in a calculator. Press SD. If you get a fraction, you get 8.83 recurring. And that is our power rating. We're going to keep it as an unrounded number because we're going to use this number in subsequent calculations. Do not round until your final answer. For some reason, the mark scheme does encourage you to round, and then it uses the unrounded answer in the rest of the calculation. Don't do that. If you worked out the power like this, don't round it. You only round your final answer. Don't do it at the very start. Bad practice. Anyway, we're now going to we need to find a relationship between current and power. Now, we know that the power of an object, another equation for it is IV, voltage times current. Now, we have not really got much information or enough information to work out voltage, or if we did, it'd be a bit of a job. What we do know, however, is that these lamps are exactly the same as before, because we're told it's the same 3 lamps that are suddenly now working. So if we don't know the voltages, we do know the resistance, because the resistance won't have changed. There's been no mention of the thermal effects of resistance, and so we're just going to assume that our resistance of bulb D is 3.3 still. Now this time we are going to use the rounded answer because that's the one they gave us to show that we were using. So it's given us that value because if you got it wrong, you need it for this one here. So if we have resistance and we have, we're trying to work out the current, what we can use is V equals IR and substitute that in for this V here, which then gives us P equals I squared R. So now we've got an equation with power, which we've just worked out, with current, which is what we're trying to work out, and resistance, which we worked out in part B. And so to work out current, I'm going to do some rearranging, divide it by R, then I'm going to square root both sides to get myself I is equal to the square root of P over R, or the square root of 8.83 recurring divided by the resistance, which I just looked up and forgot, which is 3.3. And we'll type that into the calculator and we'll get ourselves an answer. Now, with this, when you're doing this, you are going to have to use the recurring button. So I'm going to open up my square roots, get my fraction in there, 8.8. Then on these Casio calculators, I don't know how you can see this, not very well apparently, your recurring button is this shifted one up here. For me, it's on the x squared. I don't know where it will be on yours, but you're looking for the one with the dot above it. So you're going to press shift, that button, and type in the 3. And you see that you've got your 3 with a little dot above it, which means 3 recurring forever. Then on the bottom of your fraction, you've got 3.3, press equals, and you work out that your current through D is 1.636 amps. So we've worked out the current through bulb D with all these calculations, because we were just using the power of bulb D. All of these values are just for D. P of D, I of D, and R of D. So this hasn't been the circuit values, these have just been the values for bulb D. If we go back on to the other side to our diagram, the final step, because going back to the question, we're told to work out the total current in the circuit, not just the current in D. Over here, pretend this has been unscribbled out, this is why you shouldn't scribble stuff out with pen. If you go back to this diagram, the current here was twice as large as the current on this side, because as before, there are 2 light bulbs on this side, now they're all working again, and so the current here is half the value here. Therefore, the total circuit current, as before, is the 2 branches added together. We don't know what the other branch is, but we know that it's going to be half of the D branch. So you can either work out half of this and add it together, or to work out the current in the circuit, not the current, I of circuit is this value, times by 1.5, 3 halves, or 1.5. And remember again to use your unrounded answer in your calculator. Don't use 1.6 times 1.5 gives you 2.45, which rounds to 2.5. 454 amps, which gives you 2.5 amps total. Now, if you do use the rounded answer, 1.5 times 1.6 on its own gives you 2.4, and it doesn't round up. So you will not get the right answer if you use a rounded current here. This is why it's so important to always use the raw values. Don't turn your calculator off until you're done with the question completely. Just leave the answer button chilling there, ready to be used whenever you need to. Oh, and check how to get the recurring decimal number button on your calculator. If you don't know how, you can just use this fraction and put it instead of the power. So where you had the power down here, this, I'll do it in a different color. This equivalently could have been ID. You have to have multiple fractions stacked on top of each other, but you could have done 530 over 60 all over 3.3, or 53 over 6, whatever you want. But yeah, if you don't know how to get the recurring button, how to do the recurring number, if you panic, just use the original fraction. This is the most accurate form of this number. So yeah, you could do that. And it will give you the same answer, I promise. But yeah. Sorry, so for part D, all of that to the end to get 2.5 was excellence. If you got up to the point here with 1.6, that would be merit. Or if you had your power worked out correctly to be 8.8, but made a mistake in working out current, and then did 1.5 times that, whatever your answer for current was, you would get merit, including if you had 1.6 amps, if you'd rounded it and times it by 1.5 to get 2.4, that would immediately take your answer down to merit. You did nothing wrong really, but you'd go down to merit. So be really careful of that. For the achieve mark, it was just this first bit about power. You were given energy and time, so hopefully we could all work out power without too many issues. Whether you had recurring or rounded, doesn't matter. Achieve either way would be for that. Now, question 3 is about electromagnetism. Again, we've got a nice blank picture. There should be, I presume, a picture of an autonomous pesticide boom spray, whatever that looks like. A big metal rod will do. We are told, however, that a tractor with a 9.8 meter long metal sprayer, I'm going to underline metal, and 9.8 sprayer boom moves at 4.1 meters per second across a paddock. The vertical component of the Earth's magnetic field is 31 times 10 to the minus 6 Teslas. For some reason, obviously that's a typo, they haven't used standard form. That's trippy. Okay. Yeah, there you go. Sure. The vertical component of the Earth's magnetic field is 31 times 10 to the minus 6 Teslas, or 31 microteslas. So we have a big metal rod cutting through a magnetic field, which is an example we've seen before, but maybe not this particular context. Similar to an aeroplane or a bicycle handlebar going through, same idea. For part A, we are told on the diagram below to clearly label the negative end of the sprayer boom. We've got the view from above, and this is our field with the Earth's magnetic field lines drawn in. Now I'm going to do my best to use the hand rule under the camera. I don't know how much space they have. Oh, it's really close. Okay, so if this is our magnetic field, we can see the fletching of the arrows, and so the arrows are pointing into the page. So your fingers for your field, this is going to be really difficult. I'm going to lift this up a little bit. Oh, I'm like, no, I'm not. It's pointing into the page like that. Then because your tractor is moving through the field in a forwards direction, the current has a positive motion. So your thumb will end up pointing up the page. Your fingers are pointing in, your thumb's pointing up the page. So hopefully you get your palm is slapping to the left. Okay? The palm is slapping to the left. And that means that the positive charges, the current, end up on the left-hand side. We are asked to label the negative end of the sprayer boom. So if the current and the positive end is on the left, it means that the backhand or the negative end is on the right-hand side of the boom. Okay. I don't know. I'll try and add it in the edit. Showing the hand rule. I don't want to get the camera all messed up. It's okay just to set it up. But yeah. Part B. Sorry, you are using the right hand slap rule. If you're using the left hand rule, I don't know who gets taught this instead. Same idea. It'll work the same way. Calculate the voltage induced between the ends of the sprayer boom. Now we have a metal rod with a certain length moving at a certain speed through a magnetic field with a certain strength. And so we're going to use the equation to work out our induced voltage. V equals capital B lowercase v times length. And then because we're given all this information, we're just going to put it into the equation and get an answer. First one is our magnetic field strength. Now, annoyingly, it's not in standard form. If you do get one like this and it does look a bit weird, just use the number as it's given to you. Trust the paper. If they've made a mistake, or they won't have made a mistake. All the marks can be based around what they've written. So 31 times 10 to the minus 6 multiplied by the velocity, which is 4.1, multiplied by the length of the boom, which is 9.8. Put that in a calculator, all together. Don't know why I'm doing it this way, but there you go. And you should get 1.24558 times 10 to the minus 3. Sorry, you can't see that. Equals 1.2455 times 10 to the minus 3 volts. And then I'm going to round my answer, to 1.25 times 10 to the minus 3 volts. Easy as that. Part C. We're now going to explain using physics print. Oh, sorry, I probably should have explained the marking for this. So if you get the right answer, this is achieved. If you got the right answer here, this is achieved. Perhaps this wasn't clearly labelled. Negative. Missing the I. This is an achieved question. This was an achieved question. Any mistakes, you don't get any credit. Sorry, part 2 now. So how the voltage is induced between the ends of the sprayer boom. Now, because we're using physics principles, we have to explain this from the very beginning, but there's only 3 or 4 points to make. So the first one is that we need to explain why there is a force at all. The force, the electrons move and the voltage is generated or induced because the boom contains charged particles which are cutting through a magnetic field perpendicular to the field lines. That is important. They're the physics principles. So the very first point you're going to make is the metal boom contains negatively charged electrons. I'm going to just make a little reference to some chemistry. If you cast your mind back to whenever you did structure or metallic structure, in metals, electrons are free to move. If this wasn't a metal boom, if it was a plastic rod, the electrons would not be able to move, so none of this would happen. So it is important that it's a metal. So in metals, electrons are free to move. Then we say that the boom and therefore electrons are moving through a magnetic field cutting the field lines. Now, for this to happen, it doesn't have to be perpendicular to the field lines. It just so happens that this case is, and when it is perpendicular, the force is at a maximum. So just saying cutting the field lines is enough. Therefore, the electrons experience a force, and you can add according to the right hand slap. You shouldn't abbreviate RH like that, but I'm going to. According to the RH slap rule, creating a separation or a difference, I guess. A difference in charges across the rod. This leads to a potential difference or voltage. Therefore, voltage is induced. Okay, so the alternative name for voltage is potential difference. So if you have a difference in charges across something, across anything, then you also have a potential difference, which is a voltage. Therefore, the voltage has been induced by this force. Now, if you've made any one of those points, if you made the point of the boom containing negative electrons, or if the fact moving through the magnetic field cuts the field lines, or these last 2 points where you have charges moving, being separated, causing a voltage, that would be achieved. If you had 2 of those 3 points, that would be merit. Then for excellence, to be honest, you don't even need to state that in metals the electrons are free to move. I always would, because otherwise this whole thing doesn't work. But yeah, excellence is just for all of this. Part D. A wire runs along the whole length of the sprayer boom, connecting it to a warning lamp at each end. The wire is also connected to the 12-volt tractor battery. Each lamp is labelled 6 volts 3 watts. While stationary, the warning lights are activated. Clearly indicate the direction of the electromagnetic force on that part of the wire, which runs along the sprayer boom by adding an arrow to the diagram below. So this time our current is going from left to right because the positive end is over here. Now, because this end is the positive end, the bit of wire flowing through or along the boom, is going from right to left. So this time we got our field lines going into the page. Again, your thumb is going from right to left because the current is coming around this end and flowing this way. So I flows along that direction. So your thumb points to the left, which means your palm is slapping down the page. And so I'm going to add in pencil, just in case I draw it badly, my force here. Now, part 2 is to calculate the size of this electromagnetic force acting on the part of the wire running along the sprayer boom. Now, because this time we've got a stationary system, but we've got a current flowing through a field of a certain strength with a bit of wire of a certain length, we can use the equation F equals BIL. Now, we are not told what the current is. However, we are told that the lamp is labelled as 6 volts at 3 watts. We are just going to assume, therefore, that the rest of the circuit has a setup such that the light bulbs in question receive that power with that voltage. If they do, we then have enough of the equation P equals IV to work out current, which we can then put in here. So from power, if P equals IV, I equals P over V. The power here is 3, the voltage is 6, so current is 0.5 amps. If our current is 0.5 amps, we can then work out F. The field strength is the same as before, which is that janky number, 31 times 10 to the minus 6, not 16, minus 6 times by 0.5, and then the length is still 9.8, but it is given up here as well. And then we can work all of that out together. Oops. 31 times 10, oh my god, times 10 to the minus 6, times a half, times 9.8, and that gives you 1.519 times 10 to the minus 4 newtons. Which we can round to 1.5 times 10 to the minus 4 newtons. And that is your final answer. Now again, if you got the direction of your arrow as downwards and you calculated this number, that would be excellent. If you calculated this force correctly but failed to get the right direction in your diagram, that would be merit. Or if you worked out the current as 0.5 amps, or the resistance, alternatively, that is another way you could work out this question, or work out the resistance to get 12, plus the correct arrow, that would be merit. If you just did one of those things, the arrow, the current, or the resistance, that would be achieved. To work out the resistance, instead do it the alternative way. Instead of using just P equals IV, it's where you would use V equals IR in here to eliminate current So instead, before we eliminated, I think we eliminated voltage, but this time if we have V equals IR and we want to get rid of current instead, because we don't know what that is, then you can do so such that I is equal to V over R, so substitute that into here instead. You get P is equal to V squared over R, and then you can work it through as before, yada yada yada. Either way, you get 1.5 times 10 to the minus 4, and that's the paper.